Yeah.
All right. So, dear colleagues, welcome to the IFS Seminar. Today, I'm happy to introduce you my friend and colleague Matteo Capoferri of Cardiff University, who will tell us about invariant subspaces of elliptic systems. Matteo has spent his bachelor's and master's in University of Pavia, and then he has done his PhD at University College London in spectral theory and microlocal analysis. So, yes, please, Matteo, you can begin your talk.
Oh, thank you very much. Thanks for the kind introduction and invitation. Yeah, as Gira told, I'll talk about invariant subspaces of elliptic systems. I've been told that the audience will not comprise analysts only or experts in microlocal analysis and spectral theory. So I will take it gently from the beginning, introducing some basic definitions and the notions that we will be using, and then presenting the idea of, or somehow the essential ideas of the results towards the very end of the talk. But if I mention something that any of you is not familiar with, please interrupt me, and I have a board here. I can write some stuff and explain further. So the main topic is understanding invariant subspaces of elliptic systems. So it's subspaces of the domain of a differential operator that is a system, such that when we act with the operator, we remain within that subspace. There are several reasons why we're interested in this question. And in the first part of the talk, I'll try to explain why this is helpful. Now, before starting, let me introduce the setting we will be working in. So throughout this talk, we will be working on a connected, closed, smooth manifold, so compact and without boundary. So this makes life very much easier. And we denote the dimension of the manifold by d, and we assume it's greater than or equal to 2. Something can be done in dimension 1, but it's a bit annoying, so we just forget about it for the sake of this talk. We denote local coordinates on our manifold by x1, xd. In this talk, we work with n columns of L2 complex valued half densities over the manifold. So what does this mean? So an m column is an object f, which has m components, f1, f2, fm, and each of these components is an L2 half density. Half density, it means that it's almost a scalar function. Only when you change coordinates on your manifold, it transforms as the square root of a density. So if you have a metric on your manifold, you can, for example, a Riemannian metric, you can define the Riemannian density. And if you change coordinates, the half density picks up the square root of the Riemannian density, for example. Why do we want to work with half densities as opposed to scalar functions? It doesn't really matter if we work with half densities or a scalar function in the end, but working with half densities is convenient because we have a canonically defined inner product on L2. If U and V are two half densities, we can define an inner product by just taking U star V, where U star denotes Hermitian conjugation. And you see here we just integrate against the X. We don't need any Riemannian density or any other density whatsoever. Because U star is a half density, V is a half density, so their product is a density, and this is well defined. And so this integral is well defined over the manifold N. All right. And the operators we will be considering in this talk will be classical pseudo-differential operator of order S, which are elliptic and self-adjoint. I'll define all these objects in the next slide, but I'll just say that elliptic will mean that the determinant of the principal symbol of the operator is nowhere vanishing. And self-adjoint means that they are self-adjoint in the usual sense with respect to the L2 inner product as operator from HS to L2, where these are the usual Sobolev spaces. only they're not scalar functions, but are n columns. Each entry is an HS function, and for each entry is an L2 function. And this will be a system that an m by m operator that maps an m column to another m column. If you work with scalar operators, the ellipticity condition usually tells you that the principal symbol is either strictly positive or strictly negative. Say the Laplacian or the square root of the Laplacian, these are elliptic operators, so say for second order operators. When you work with systems, you don't need to require that the determinant is strictly positive or strictly negative. We just require that it's nowhere vanishing. So it's a weaker condition, if you wish, when you work with systems. So ellipticity, it's a weaker condition. Now, a reminder of the notions and concepts I just mentioned. So if you have a differential operator, say a partial differential operator will be an object like this, where you have derivatives, partial alpha, with some coefficients, smooth coefficient C alpha x that depends on x. So this is a canonical form of a differential operator. And if you sum derivatives up to order s, so if the highest derivative appearing is of order s, you say that the operator is an operator of order s. Say the Laplacian is a second order operator because we have two derivatives. And given a differential operator, one can associate, one can construct its symbol. And its symbol is constructed by formally replacing each derivative with I times momentum, I times psi mu. And what we get will be a polynomial in psi with coefficients which will be the smooth functions that we had before. And for a differential operator of order s, the symbol will be a polynomial in psi, in momentum, of degree s. Now, the top power of this polynomial, so the highest power monomial in this polynomial is called principal symbol, and we call it AS. And the subleading term in this polynomial is called subprincipal symbol. So the subprincipal symbol is the subleading term plus a correction. So it's not exactly the subleading term, and the reason is the subleading term is not invariant. If you change coordinates, this guy changes. So Doistermatt and Hormander realized that in order to make the subleading term invariant, you need to add a correction to it that comes from derivatives of the leading term. And if you do so, you get an invariantly defined object. If you have a first order differential operator, principal and subprincipal symbol completely determine your operator. If you know them, you know everything. If you know the operator, you can compute its spectrum and so on. For other operators, this is no longer true. So for example, if you work with the Laplace-Beltrami operator on half-densities, you assume now your manifold carries a Riemannian metric, and you know that the Laplace-Beltrami operator has this structure, this expression. And you can formally perform this substitution, compute its symbol, and you will find out that the principal symbol is minus the norm of momentum squared, the Riemannian norm of momentum squared, and the subprincipal symbol is 0. It's just a calculation. And you see the principal symbol will be a homogeneous polynomial of degree 2. Now, this works for differential operators. We will not work with differential operator, but we will work with pseudo-differential operator. It's more or less the same, and you can disregard the pseudo bit in the rest of the talk, and everything will work fine. But pseudo just means that the symbol will no longer be a polynomial, but it will be a polyhomogeneous sum. It means that we can take the symbol and we can decompose it in polyhomogeneous components as minus k, meaning that the component s minus k will be positively homogeneous in momentum of degree s minus k. Say if we scale momentum by lambda, we get lambda to power s minus k. You see, for polynomials, each monomial term is homogeneous of the corresponding degree. So this is homogeneous of degree 2. But you can construct homogeneous functions which are not polynomial, and polynomials, and if you do so, what you get are pseudo-differential operators that are natural generalization of what we had before. Instead of having homogeneous monomials, we have homogeneous functions of x and xi, which would be more complicated. And if we work with systems, these functions will no longer be scalar functions like here, but they will be m by m matrices, where each entry has this structure. Each entry will be a polyhomogeneous symbol, this form. So any question up to here? Comments, remarks? All right, you can think about differential operators and everything will work. So we now have our m by m pseudo-differential operator A that we are working with, and we assume throughout this talk that the principal symbol has simple eigenvalues. So the principal symbol will be a matrix function on the cotangent bundle. And since the operator is self-adjoint, this will be a Hermitian matrix. So it will have real eigenvalues. And we assume that these eigenvalues are simple at every point in the cotangent bundle. Some notation. So we denote by m plus the positive eigenvalues of the principal symbol, and by m minus the negative eigenvalues, number of negative eigenvalues of the principal symbol. We denote the principal symbol themselves by hj, and this reminds us of Hamiltonian, because these will be interpreted as Hamiltonians in the cotangent bundle later on in the talk. And we enumerate the eigenvalues of the principal symbol in a very particular way. So we denote by them by hj, and we choose positive j for positive eigenvalues and negative j for negative eigenvalues. These eigenvalues will be themselves scalar functions on the cotangent bundle. And since the operator is elliptic, if they are positive at one point in the cotangent bundle, they are positive everywhere. And if they're negative at one point, they will be negative everywhere. So these numbers, m1, m plus, and m minus are constants and well-defined. And this enumeration is also well-defined, because if it's positive at one point, it's positive everywhere. And we denote by pj, capital Pj, the corresponding eigenprojections with the same enumeration. So hj's are the eigenvalues of the principal symbol, pj's are the eigenprojections of the principal symbol. So just the application of the spectral theorem for Hermitian matrices tells us that the eigenprojections sum up to the identity, and that the principal symbol can be written using the spectral theorem as the sum of the eigenvalues times the eigenprojections. And this will be m by m. Each of these is an m by m rank 1 matrix function. Any questions about the notation? All right, an example that somehow will set the motivation for the talk. So an operator like the one we are discussing is, for example, the massless Dirac operator. So what is the massless Dirac operator? So suppose now we are working on top of the assumptions I mentioned before. Assume that our manifold now is a 3 manifold, so of dimension 3. It is orientable and it carries a Riemannian metric. So an orientable Riemannian 3 manifold. On such a manifold, so since this manifold is orientable and it's a 3 manifold, it's automatically parallelizable. So we have 3 orthonormal global framings that we denote by EK, K1 to 3. And we denote by SK, K1 to 3, the usual Pauli matrices. Then we can project the Pauli matrices along the framing in this way to construct the matrices sigma. So EK alpha is the alpha component of the kth vector field of the kth framing, and we sum over K with Pauli matrices in this way. This gives us vector valued matrix functions on the cotangent bundle. So these are matrices with the vector index sigma alpha that transforms like a vector under change of coordinates. And the massless Dirac operator that probably most of you are familiar with one way or another can be written explicitly as a 2 by 2 matrix differential operator, which has precisely this form. So this is a 2x2 matrix where each entry is a differential operator and can be constructed explicitly using the sigmas we defined before and Christoffel symbols, because we're working on a curved manifold. And this is the expression you get. You can compute explicitly the principal symbol. And again, you're probably familiar with it. So this is the principal symbol at a given point in a specific coordinate system. This is why I have a star here. But okay, more or less, this is the structure of the principal symbol everywhere. And probably you're also familiar with this one way or another. And you can see somehow that Pauli matrices are hidden in here. Here we have 1 minus 1, 1, 1, minus I. So Pauli matrices sit in there. We can compute the determinant of the principal symbol, and again we see that the determinant of the principal symbol is minus the norm of momentum squared. In the eigenvalues, we have one positive eigenvalues, and we will denote it by H1 with the notation we introduced before, and one negative eigenvalue that we denote by H minus 1, again with the notation we introduced before. So this is the massless Dirac operator. And this is an example of an operator that somehow has a right to be considered within the assumptions we gave before. So this is an interesting example we want to study. Now, suppose you have the Dirac operator, you want to write down the Dirac equation. And the Dirac equation is this equation here. So you can take your Dirac operator W, which is elliptic, you complement it with time, you add minus I the t, and you write down what is known as the Dirac equation, the massless Dirac equation. And this gives you a propagation in time with some initial condition, v at t equals 0 equals v naught. So v will be a smooth function on time with values in h1, and v naught will be some h1 initial condition. All right. Once you have the Dirac equation, you would like to solve it. So how does one solve the Dirac equations? There are various ways. One way to do it is to construct the so-called propagator. So the operator which is e to the minus iwt, where w is the Dirac operator. This is a one-parameter family of unitary operators that can be written down explicitly using the functional calculus in terms of the eigenvalues and eigenfunctions of the Laplace of the Dirac of the Dirac operator. And this operator is the solution operator of the Dirac equation. So if you know u of t and you apply u of t to your initial datum, you get a full solution, where full means including time, of your Dirac equation. So u of t times v naught will solve this equation here. So knowing the propagator is helpful in solving hyperbolic equations or analogs of them. But propagators are useful also for other reasons. If you look at this expression here for the propagator, you see that eigenvalues of the operator sit inside the propagator somehow. The propagator knows some information about the eigenvalues of your operator. And one can show it is actually not too difficult an argument. I can explain how one does it at the end if people are interested. That if you study the small time behavior of the propagator, so if you understand how u of t behaves for t tends to 0, this gives you information about how the spectrum of the operator behaves for eigenvalues that tend to infinity. So the behavior of large eigenvalues of the operator are given by the behavior for small times of the propagator. So knowing the propagators on the one hand allows you to solve the equation you're interested in, for example, physically meaningful equations like the Dirac equation, and on the other hand allows you to study the spectrum of elliptic operators. I mentioned the Dirac equation here, but there are a lot of physically meaningful examples that fall in this category. We want simple eigenvalues, so we are somehow restricted here, but we still have the elasticity or Lamé operator, we have the Dirichlet-Neumann maps, and the number of other meaningful operators that one can study within this framework. So one can formulate the problems more abstractly. So if one doesn't have the Dirac equation, one can go, the Dirac operator, one can go back to a more general first order operator A, like the Dirac operator, write the same kind of equation and construct the propagator in the same way. And for any such given first order operator, one would like to understand what the propagator looks like. And the natural question is, can we write down the propagator explicitly? Can one write down this u of t somehow? Okay, a formula was in the previous slide, but in order to write this down, one needs to know all eigenvalues and all eigenfunctions of the operator, which is unrealistic. Nobody knows them, barring very highly symmetric cases and very specific operators. But even the Laplacian, you don't know how to do it if you have a closed manifold. So an idea that somehow has been around for many decades now is to use Fourier integral operators, namely to construct the propagator as an oscillatory integral. Say, if A was the square root of the Laplacian and you were in Euclidean space Rd, you would write solution using the Fourier transform, and you would write down, say in your undergraduate course on PDEs, an expression like this, just by Fourier transforming the equation and integrating against the initial data. Fourier integral operators are just a more complicated version of these, where this function at the exponent, which is called phase function, is now allowed to be a more general function of t, x, y, and eta. And instead of integrating against one, you allow to integrate against the slowly oscillating function a of time and y and eta. There are a lot of construction, a lot of classical ways of constructing these oscillatory integrals that go back to Hadamard, Hormander, Trev, and so on. One can ask questions about, can one do this invariantly? Can one do this globally? But this is, the answer is yes, but this is the topic of a different talk. I won't discuss it here. I now just want to give you a flavor of how one can construct these objects locally, because I will need this as motivation for what comes next. So suppose I give you an operator A and you want to construct the propagator. How do you do that? So the way you do that is the following. So you look at the principal symbol, which is this matrix. You can compute it very easily. And you compute the eigenvalues of this principal symbol, your HJs. And you interpret these eigenvalues as Hamiltonians in the cotangent bundle. And you write down Hamilton's equations in the cotangent bundle associated with each of your eigenvalue of the principal symbol. So for each Hj, you write down the Hamiltonian system, and this gives you a Hamiltonian flow on the cotangent bundle associated with that eigenvalue. And we can denote this, the Hamiltonian flow, by H, xj and xij. This will be associated with the j eigenvalue. T is the parameter along the flow, and y eta are the initial condition of your Hamilton's equations. Once you do that, you can construct functions phi that eventually we will want to put here that are compatible with that flow. And compatible means that they have to satisfy a certain number of conditions to incorporate information about this flow. So they will have to behave nicely along this flow. And the reason for this is that these functions phi, these phase functions, will incorporate information about the propagation of singularities of your equation. If you look at this oscillatory integral, you realize that the stationary points of your phase give you information about the singularity structure of this operator, the same way that this happens for the Fourier transform. So you want to incorporate into your function phi the right singular structure associated with your operator, and this is given by the Hamiltonian flow of the eigenvectors of the principal, eigenvalues of the principal symbol. And once you do that, you can write the propagator as the sum of precisely m oscillatory integrals, one for each eigenvalue of the principal symbol, where this phi is the function that contains information about the flow of the jth eigenvalue. And then there is a way to construct this complicated function here once you have fixed your phi. There is an algorithm, you just follow the algorithm, you solve ordinary differential equations, and you work out what this function here should be. You can just think of it as a single function, forget about this, that there are many terms. It's irrelevant for the time being. But this is a general idea. Principal symbol, eigenvalues contain information about the propagation of singularities. You compute the flow, you construct functions phi's that are adapted to that flow, and you construct the propagator as the sum of m oscillatory integrals, one for each eigenvalue. You sum them up and you get your propagator. You get your propagator approximately up to an infinitely smoothing operator. So what you're missing out is an infinitely smoothing operator. What does infinitely smoothing operator means? It means an operator that takes a function f and maps it to integral of, okay, let me write it down because this is important. An infinitely smoothing operator is an operator that acts on a function f and acts in the following way. Is the integral of k of xy, f of y, in dy over your manifold, where k is an infinitely smooth function in both variables. These are very nice operators, are compact operators, are trace class. They enjoy a lot of wonderful properties. And we can construct the propagator explicitly, being prepared to miss out a contribution like this. But this is no big deal if one is interested in propagation, in capturing the singular structure of your solution. And then our colleagues in numerical analysis can reconstruct the smooth bit somehow, or so they claim, but we trust them. And for practical purposes and for proving theorems, usually the non-smooth bit, so this sum of UJs is more than enough. And this sum of UJs is definitely more than enough for studying the spectrum of the operator in the way I mentioned before. Any questions up to here? Am I going too fast? Okay, I see. Girard says no, so I'll carry on. All right. Yes, I now want to give a bit of basic information about the spectral theory of A, and the motivating bit is almost finished, a few more minutes, and then we'll get into the meat of the talk. So I now want to give, to set a few rudiments in spectral theory of systems. So how does the spectrum, what does the spectrum of a system looks like? So we are working on a closed manifold, so compact and without boundary, and we have an elliptic operator. Then the resolvent is compact, so the spectrum is discrete and accumulates to plus or minus infinity or both. More precisely, if we have at least one positive eigenvalue of the principal symbol, you can show that the spectrum accumulates to plus infinity. And if you have at least one negative eigenvalue of the principal symbol, you can show that the spectrum accumulates to minus infinity. So the sign of the eigenvalues of your principal symbol tells you whether the spectrum goes away to plus infinity or to minus infinity or to both of them. But the spectrum is definitely unbounded, at least in one direction. How unbounded it is qualitatively given by the sign of the eigenvalues of your principal symbol. So principal symbol contains a lot of information about your elliptic system. So now let us denote by lambda 1, lambda 2, and so on, all the positive eigenvalues of your operator. And let's suppose that there are infinitely many of them. So let's suppose that m plus is greater than or equal to 1 without loss of generality. If it's not, you can just take minus the operator and then this will be satisfied. We can construct what is known as counting function, n plus, or eigenvalue counting function, n plus of lambda, that is 0 if lambda is less than or equal to 0, or 1 if, or the sum of the eigenvalues from 0 to lambda if lambda is greater than 0. So it tells you how many eigenvalues, positive eigenvalues you have below a given lambda. And this is a discrete function that has a jump whenever you hit an eigenvalue. Now, The first bullet point gives us a qualitative behavior of the spectrum. Now we have a quantitative behavior. So this discrete function can be approximated when lambda becomes very large by a smooth function or by a polynomial asymptotically. And this is known as Weil's law. You know that the number of eigenvalues below lambda behaves like some explicit coefficients that can be computed times lambda to power dimension over order of the operator, d over s. This is the dimension of your manifold, s is the order of your operator. So if you have the Laplacian, this would be d over 2. Plus little o of the leading term. So this is the Weil law with rough remainder and tells you quantitatively how your eigenvalues behave for large lambda. One can go further and make the second term explicit, and this has been computed recently, relatively recently by Chervova, Downs, and Vasiliev in 2013, and the different proof was provided by Girard, Vasiliev, and Shostran a few years ago. I don't want to discuss this formula. I just want to point out that the second term in the asymptotic expansion was obtained only recently. And this testifies to the fact that doing spectral theory for systems is much more difficult than doing spectral theory for scalar functions. It's not just a matter of taking a bunch of equations and putting them together and you just do the same thing several times. There are truly novel phenomena, mathematical phenomena that happen there. And there are challenges that one needs to overcome. And the fact that this formula was obtained only in 2013, where the first formula was obtained, I don't remember the year, but I think in the 60s, for scalar equations by Doistermatt and Guillemin, is an indication that somehow it took several decades to move from scalar functions to first order systems, scalar operators to first order systems. All right, now let us go back for a second to propagators now. All right, so we said that the propagator, we saw the propagator before, right? Now we can define positive and negative propagators by summing over the spectral decomposition over positive or negative eigenvalues only. This gives you the propagator associated to the positive spectrum of the operator, and this gives you the propagator associated to the negative spectrum of the operator. And your propagator will be the sum of the two. And what we have shown a few years ago, a year ago or something, building upon earlier results by Safarov and Vasiliev, is that the positive propagator is approximated by the sum of the oscillatory integrals, ujt, corresponding to positive eigenvalues of the principal symbol. And the negative propagator is given by the oscillatory integrals associated with the negative eigenvalues of the principal symbol. So positive eigenvalues give positive spectrum of the operator, negative eigenvalues of the principal symbol give negative spectrum of the operator, and a similar decomposition exists at the level of the propagator. Positive eigenvalues allows you to approximate the positive propagator, and negative eigenvalues of the principal symbol allows you to approximate the negative propagator. Now, yes, so here is the summary. So now the question is, can we do better? Can we do better? So we said that, positive eigenvalues of the principal symbol accounts for the positive spectrum of the operator, and the same thing for the negative ones. But now the question is, so suppose we have two positive eigenvalues of the principal symbol. Does each of those account for a subset of the positive spectrum or not? Is there a way to associating some of the eigenvalues to one, some of the eigenvalues of the operator to one of the eigenvalues of the principal symbol, and the same thing for the other? Say, can we decompose the positive spectrum, which is this infinite sequence of eigenvalues, into two infinite families, one for each eigenvalue of the principal symbol? In other words, can we say each of these uj of t, what part of the spectrum does it account for? So what is this uj of t? Can we express it in terms of the functional calculus? Can we say what this uj of t describes of our operator, or can we only say that the sum of the positive ones gives us the positive spectrum? So can we refine this analysis? So this is an interesting question because it will lead us to understanding invariant subspaces for elliptic systems. It will give us a better understanding of spectral asymptotics, and at the same time, it will give us a refined information about propagation of singularities, because we will know what each of these uj of t is about, what's its deeper meaning. And a key technical ingredient, so a key construction to understand better the spectrum of elliptic operators are pseudodifferential projections, and I will now go on to describe them. So here ends the motivational part and somehow the bigger picture, and we now move on to the core of the talk, so the topic I wanted to discuss about, which is understanding invariant subspaces of elliptic systems. And the reason why we want to do that is because this allows us to study the spectrum, but it has a reflection at the level of the propagator of physically meaningful operators. So we can understand solutions of physically meaningful equations better. So it's not just a mathematical question that comes from pure analysis, but it has concrete applications. All right, so yes, I should mention that the talk is joint work, what I'm going to talk about is joint work with Dima Vasiliev from UCL, and it's based on two recent preprints from March this year, which are mentioned here, and some of the bits, maybe towards the very end, if I have the time, may come from a number of previous earlier papers that are listed here. So what are pseudodifferential projections? So all of you are used with usual projections or orthogonal projections on a finite dimensional vector space. Here we're just generalizing it to infinite dimensional vector spaces. And in particular, these will be operators on L2. So we say that an operator, a zero order operator, is an orthogonal pseudodifferential projection if it satisfies these two conditions. So p squared equals p and p star equals p. So if it's orthogonal and idempotent. Modulo psi minus infinity, where modulo psi minus infinity means, as before, up to an infinitely smoothing operator. So an integral operator with infinitely smooth kernel. And you see, these are the conditions that you usually have for projections. We just now promote them to operators. And these act on infinite dimensional spaces. They act on L2, on m columns of L2 functions. And we generalize the notion of an orthonormal basis and we promote it to an orthonormal pseudodifferential basis if we have m orthogonal pseudodifferential projections such that their principal symbol are rank 1, so they are rank 1 matrix functions, and they are orthogonal to each other and sum up to the identity. And these are, again, familiar definition, just promoted to operators, and everything is modulo psi minus infinity, because we work with pseudodifferential operators. Now, any questions about these definitions? We're just promoting the concept of projection in a finite dimensional vector space to the level of operators, and these will act on L2 functions. So this is an infinite dimensional space. Now, the first question is, do such operators exist at all? Which is not obvious. If they do exist, can we choose them in such a way that they furthermore commute with the operator A, so that we have a chance of defining some sort of invariant subspaces for this operator? And again, we require this condition modulo psi minus infinity. And we here require that the principal symbols are precisely the eigenprojections of A, so that these operators are adapted to our operator A in an optimal way. Can we do that? And final question, if we can do 1 and 2, does this define these operators uniquely or not? You see, already existence of a single pseudodifferential projection is not so clear. Because if you look at this condition and you try to write down what it means at the level of the symbol, you get an infinite sequence of heavily overdetermined problems. already the first equation is heavily overdetermined. You just look at it and you say, all right, this is already heavily overdetermined, and I have a bunch of them to satisfy after this one. Will it be possible? Will it not be possible? And again, since we work with pseudo-differential operators, modulo psi minus infinity, we cannot really determine them using functional calculus. We really need another way to do this. So it's more sophisticated. It's more sophisticated than just saying use eigenvalues and eigenfunctions of your operator A and do something with them. You cannot do it. It's hopeless because of this thing. Okay, here is a bit of history, which I will skip because I don't have too much time. Okay, there are some pseudo-differential projections appear in various forms in the literature, not always in a clear way and not always in an explicit way. One can construct them in one way or another. Biermann and Solomiak do it integrating this object here in the complex plane. Bolta and Glaser improve their construction a little bit in the semi-classical setting, but bottom line, there is no general construction for pseudo-differential projections of the type I just described. No full description of the symbol, no clear construction, and integrating over the complex plane requires additional conditions that we don't want to have. Because when you do this contour integration, your eigenvalues have to be well separated so you can encircle them. And there is another approach, which is diagonalize the operator, which I don't want to discuss either, and on which I'm writing something at the moment. So maybe in the future, you'll be able to read that. So the good news is that this horribly overdetermined system has a solution. So pseudo-differential projections do exist. So we can construct a pseudo-differential basis. And the proof is an algorithm for the construction of their full symbol. These projections are not uniquely defined, but there are a number of degrees of freedom left in the symbol. So once we satisfy this bunch of conditions, we have a lot of freedom left in the symbol, surprisingly, in spite of this problem being overdetermined. So there is a hope of using the remaining degrees of freedom to satisfy the commutation with the operator. I should mention that one can turn approximate projections into exact projection, so we can get rid of modulo psi minus infinity if you wish. So we can construct an honest pseudo-differential basis without any remainder term. Now, if you want to satisfy the commutation condition, the answer is again yes, you can do that miraculously. And if you do it, you use up all the degrees of freedom left. Once you satisfy the commutation condition, your pseudo-differential projections are defined uniquely. And as it turns out, if you require this condition, then it's enough to satisfy that p squared equals p, and orthogonality and the sum up to the identity come as a free byproduct. So if you satisfy these three conditions, these two are for free. So somehow it's a very rigid problem, and here you see that it was indeed overdetermined. And okay, it was already overdetermined to do this, but somehow you don't need all conditions to determine them uniquely, you just need some of them. And then there is some rigidity within the problem for which the other two counts for free. And the proof is again using up the degrees of freedom. Now, why are these operators useful? The reason is that this condition and this condition and this condition imply that if you take Pj, you act with the pseudo-differential projection Pj on L2, and then you act with the operator A, you remain inside the same subspace up to modulo C infinity, up to infinitely smooth functions. So this tells you that Pj project onto almost invariant subspaces of L2 for your elliptic operator A. It is known that given an elliptic operator, it's not guaranteed to have invariant subspaces. But what this construction shows is that it always has m almost invariant subspaces uniquely determined by the operator itself. And an observation here, if we can drop the modulo psi minus infinity in the construction of projections, we cannot drop it here. Somehow requiring the commutation condition tells us that somehow modulo psi minus infinity is needed. We cannot turn them into honest projections and satisfy at the same time the commutation condition. All right, so as I said before, we have an explicit algorithm. Everything can be computed explicitly. And these pseudo-differential projections are really non-trivial objects. And again, I show a formula here to give you a feeling that somehow these are non-trivial objects. And mistakes in the spectral theory of systems came from failing to realize that somehow these objects have a non-trivial structure. But I don't want to say more about that at the moment. Now, in the study of the spectral properties of the operator A, we can use pseudo-differential projections to decompose our system into m sign-definite operators, modulo psi minus infinity. So if you take pseudo-differential projections corresponding to positive j and you sandwich the operator, you conjugate the operator, you get a non-negative operator. And if you do it the same for the negative one, you get a non-negative operator, a non-positive operator. So this is the first step towards understanding how the spectrum can split into series of eigenvalues. The trouble is here that these operators Pj, A, Pj are not elliptic, so proving this positivity condition is not trivial. All right. Yes, okay. An immediate consequence of our construction is that one immediately has that the theta function of an elliptic system and the modulus of an elliptic system are pseudo-differential operators. And as a corollary of our algorithm, we can describe their full symbol, just like that. So we have an explicit description of them in terms of pseudo-differential projections. Well, these formulae again are kind of obvious now once you see the properties that pseudo-differential projections satisfy, but you still have to prove them. And somehow you can get nice formulae that nobody knew before and use them to do useful stuff. All right. Now that we have these pseudo-differential projections, so these projections in the space of L2 that decompose L2 into m subspaces, approximate subspaces. What can we do with that? So what can we say about the spectrum of the operator? So suppose you have at least two eigenvalues of positive eigenvalues of the principal symbol, so that we can understand whether each of them, what's the contribution of each of them. If you have only one, there is nothing to partition to begin with, so we don't have anything to do. So let's suppose we have at least two of them. And we want to partition the positive spectrum into m plus series of eigenvalues of the operator. So how do we do that? Naively, one could think, okay, you look at the previous slide, you have these operators here, and just you look at their spectrum. Problem is, these operators are not elliptic. So looking at their spectrum is very painful. And all the elliptic results do not work, so we're in trouble. So we have to come up with a clever idea. And the idea is the following. We observe that we can write the operator A as the sum of L operators using pseudo-differential projections, right? Now, why is this equality true? Okay, PL and A commute, so we can bring it. You can bring PL on this side. Now PL star equals PL. PL squared equals PL, and sum of PLs is identity. So this A equals this sum. And what we want to do if we want to study the spectrum, we need to construct elliptic operators out of this object. And what we do, we take the operator A and we subtract twice PL APL for positive L. So at the level of the principal symbol of the operator, what we are doing, we are flipping all eigenvalues of the principal symbol except the jth one. So AJ will be a simpler operator, it will be elliptic, but it will have only one positive eigenvalue. So we know that all the positive spectrum of AJ is given by this eigenvalue HJ, right? But okay, and the hope is that the positive spectrum of Aj, if we sum them all up for positive j's, will give us the spectrum of the operator. Problem is doing these transformations, so subtracting this term from A messes up A pretty massively. So a priori, we do not have guarantees that this preserves the spectrum at all. It might be messing up the spectrum massively as well. The reason why there is hope that this doesn't mess up the spectrum too much, if we look at what happens, so the properties of these operators Aj, and we drop the modulo of psi minus infinity, using just operator theory for unbounded operators, we see that the spectrum, the positive spectrum of A, is precisely the sum of the positive spectra of the Aj. So we have a precise identity between spectral projections. You just look in Schmutgen's book and you play around with the theorems there for a little bit. So there is hope that when there is modulo of psi minus infinity, we can prove something as well. But this is much more delicate. It's a much more delicate construction. So here is the abstract operator theoretic argument, which I don't want to discuss. But this gives you a precise identity between spectral projections. If you drop the modulo of psi minus infinity and you have operators that satisfies the properties that our operators satisfy. All right, so okay, we can prove some theorems about the spectrum. I don't want to discuss them too much because somehow we don't have experts in spectral theory here, so they're probably not interested too much into the details of the spectral argument. I will just give the main result, which tells you that if you take these operators Aj, so this Aj that we had before, and you combine them, so you take the Aj for positive j, and you combine their positive spectra into one single sequence that you call mu1, mu2, μk. Then you can prove that the positive eigenvalues of the operator A lambda k are precisely the eigenvalues μk up to a shift R alpha that depends on how good a remainder you want to get. For any alpha negative, you can find a shift such that lambda k is mu k plus R alpha with this remainder as k tends to plus infinity. So this tells us that if you sum up the eigenvalues of the operators Aj, you reconstruct the positive spectrum of A precisely. So we have decomposed the positive spectrum of J into A into n plus series of infinite series of eigenvalues of the operator, one for each eigenvalue of the principal symbol. Okay, and here is the argument in the proof, but I don't want to discuss it unless people are interested. Now let's go back to propagators, because this gives, we wanted to understand somehow solutions of our hyperbolic equations, right? Okay, spectral theory is interesting, but from the physical point of view, solutions are more interesting, propagators are more interesting. If we now go back and we look at this, we can characterize these oscillatory integrals and understand them much better. For example, we know that if we evaluate these oscillatory integrals at t equals 0, these are precisely the unique pseudodifferential projections that were given by our theorem. Furthermore, we know that if we take the k oscillatory integrals and we project along, we precompose with pj, so we project along the jth invariant subspace, we get 0 unless we are propagating with the jth oscillatory integral. So each of these uj propagates within the almost invariant subspace. So if you start within the invariant subspace, your propagation keeps you in that invariant subspace. So this tells us that pseudodifferential projections decompose L2 into almost invariant subspaces under the action of your operator A, but also under the action of your evolution, of your hyperbolic evolution. So these are invariant subspaces under that evolution as well. And the jth propagator is simply the projection of your full propagator composed with the projection onto the subspace corresponding to Pj. And here is what I said before, yeah, that if we start with the initial data within an almost invariant subspace of L2, the hyperbolic evolution keeps you within that subspace. Yeah, I've finished. So this is my last slide. I will just say that now we have a way for refining spectral asymptotics for systems. We can study spectral asymptotics along each of these invariant subspaces. And this will give us asymptotic formulae for the counting function for each of these uj. And we know that these will be the positive eigenvalues of a given elliptic operator that can be described explicitly. This is the technical statement of the theorem, but it's not important. It just tells us that once we have invariant subspaces, we can now translate information about propagators for small time into information about large eigenvalues and compute spectral asymptotics. All right, that's I think my time is up. So yeah, 6:57. So thank you very much for your attention. And if you have questions, I'm happy to elaborate more on various aspects of what I said. Thank you very much.
Thank you, Matteo, for the beautiful talk. So, and now we have enough time for as many questions as we wish. So, yeah, we welcome everyone to ask their question, please. So maybe I can ask a question to sort of open the discussion. Right, so the distances between the union of individually produced spectra and the original spectra, so that's what you take as the measure of closeness of the synthetic spectrum and the original spectrum, right? Do you think there might be some other measures of how good that approximation is? For instance, in terms of the counting functions, distances between counting functions, something in spirit of Kolmogorov distance between cumulative distributions or so?
I thought about it, but I don't think it's realistic. And the problem is the following, you see. So, okay, when you prove this closeness, first you prove the closeness. You take the eigenvalues of Aj and you show that the spectrum of Aj is very close, k minus infinity, to the spectrum of A.
Right.
And then the other way around. The spectrum of A is very close to the spectrum of Aj. And then you want to prove something about individual eigenvalues. When you start proving something about individual eigenvalues, the issue are spectral clusters. You see? The spectra as set might be very close, but one of the two operators might have eigenspaces with very, very high multiplicity.
Right.
So the closeness of the spectra doesn't see the high multiplicity of the spectral cluster. And this is why here we have k minus infinity, and here we have k alpha, because of these spectral clusters. And if you want to prove a closeness of counting functions, these counting functions might have massive jumps because due to these spectral clusters. So there is no obvious way of relating spectral functions, counting functions for this reason. This is why I didn't state the theorem for counting functions. Maybe there is a way, but we thought about it for a while and we couldn't find a way. And probably it's impossible to express, to write a simple relation because of spectral clusters.
Thank you. Maybe once we are in that topic, so let me ask a further question. This one may be a much more naive question, but anyway. So you wrote something about the local counting functions, and I was wondering if this decomposition into where was it? Yeah, so if this decomposition of local counting functions into a sum over a particular local counting functions corresponding to particular eigenvalues of the principal symbol, does this help to do the standard thing that when we work on, say, a non-trivial vector bundle instead of columns of half densities, you just, sum up the local ones with the partition of unity, and you get the overall. And does this thing now survive that possible patching, or
yes.
does it work smoothly?
Yes, it does.
Good.
We didn't write down the details, but I'm pretty sure it does. Yes.
Okay.
But yeah, these projections are pretty powerful objects, as we came to realize. And yeah, I'm now trying to write down something about unitary diagonalization. You can use projections to diagonalize your operator, and then you effectively relate it to m scalar operators.
Mm-hmm.
And then you have to show that the spectra of the scalar operators are closed, and then you can prove two terms asymptotics using formulae for scalar operators as opposed to systems, and you should get the same result, but you get somehow a much simpler proof. And there you see that all this patching works.
Yeah, so your projectors PG, they are, they are bounded from L2 to L2, right? Because they are zero order. Yes. And they are self-adjoint. So you can, in principle, do spectral theory and spectral functional calculus on PJs individually, right? So and begin somehow mixing spectral theory or functional calculus with microlocal approach.
You can, but as soon as A comes into the game, you cannot do that.
Yeah, right. Yeah, right.
Yes. Okay. I stated it self-adjointness modulo psi minus infinity, but you can really take, I know, I state them precisely self-adjoint. It doesn't matter. You can always make them self-adjoint. You can just change them.
Yeah, that's what I mean. And then you can do certain things with it, consider the spectral projections of PJ, and since PJ is meant to commute with A, then the spectral projections should also commute with those of A, and so on and so forth.
Yeah, but these are zero order operators, so life is not that easy. Yeah, if they were positive order, it would be slightly easier, but with zero order, it's always tricky.
Right. And maybe one more question. I think you said you are working with a similar argument with microlocal diagonalization, right?
Yes.
So, or maybe I make a small comment for those who maybe don't know why you are choosing the principal simple to have simple eigenvalues. And the point is that, unfortunately, even if the Hermitian matrix is C-infinity, its eigenvalues are only guaranteed to be C1, and eigenprojections are only guaranteed to be C0, generally speaking. So in order to make them C-infinity for sure, one way is to assume that the spectrum is simple, so that eigenvalues don't cross anywhere. But if you go down the way of microlocal diagonalization, there are some known attempts of dealing with multiple eigenvalues if you assume the microlocal diagonalization. Do you think you could probably relax that assumption of simplicity of the principal symbol if you are working already in that sort of dirty microlocal diagonalization techniques?
I don't know. Maybe one can, but with a different construction. You see, the diagonalization argument starts from these projections that are constructed using the assumption of simple eigenvalues. And you're right that there are some constructions, more general constructions, when we say you have massive Dirac, where the eigenvalues are multiple. Those are what people have been doing. But these constructions are not very clear, not very explicit. They just claim that one can do it if it does such and such things. And yeah, for Dirac, it is done in some detail, in some more detail. But in general, there is no clear construction. And I think somebody does it in a slightly more general setting, but then you have to assume that your eigenvalues are well separated, that there is a smooth function, a fixed function that bounds from below and away from zero all your eigenvalues. And this is a very strong requirement, which you don't want to have. But in the long run, possibly that's true, yes. We're also thinking about using this approach with projections to deal with, say, curl, which is multiple eigenvalues. And this might be the first step towards what you say. If we manage to deal with curl using projections, then we will see what to do there and possibly generalize it to the general case. But it's not easy. Yeah.
Thank you. So further questions, please.
There's something in the chat. Oh no, it's Claudia. Yeah. Claudia is going home. It's very late in Italy.
All right, if we have no further questions, then let's thank the speaker again and finish the formal part of the seminar.
Thank you very much.